Hi everyone. Welcome to another episode of the Common Lisp Study Group in prime time. We're back on Mondays from 8 p.m. to 10 p.m., which we did a couple years back. We'll be here weekly from now on. We did a little bit of a hiatus the last couple of weeks, but we're still going to be tuning in and continuing our discussion of student, which is the word algebra problem solver that we've been covering as part of our ongoing coverage of paradigms of artificial intelligence programming case studies in Common Lisp. Now, today we're going to be discussing specifically discussions related to some of the Chapter 7 exercises. In particular, there's one particular exercise that I wanted us to go through because, one, we've been covering various easy extensions to come to students specifically. And to give you some context here, let me pull up our student code that we were looking at from Dr. Norvik's repository, which I have kind of conveniently put here. Student, there we go. Yes. And for whatever reason, it was unable to start a Lisp. But now we are able to, and let's go ahead and do this. 1 second here. For some reason, my keyboard mapping got messed up again. There we go. All right. There we go. So last time when we discussed student, we kind of went through a couple small extensions. Originally, we added some basic extensions related to, for example, dealing with thrice, being able to write word problems where we have the word thrice and we're able to actually triple the actual value that is being passed in. Additionally, if you recall, we actually went through and solved the issue of the word problems related to implementing some of the signs related to specifically um, if we the exercises for um, which one was it? It was uh, yeah, the 7-6 examples where we were talking about handling special characters properly, and here we also talked about um, some of the basic things related to uh, getting. We also did uh, one of the other medium problems related to. Um, we did 15% less. We actually did 14 divided by 7. We've actually covered. Um, we did 7-6 mainly. Let me pull up the other thing that we actually have written here. Roswell, local projects, AFP, PAIP workshop, source, main.lisp. I think we actually have some other stuff related to this here. Do we have anything in here? Let's see. We went through, oh, these are all the search problem stuff. So we went through, 1 second. Sorry, me going into some of our backups here that we have here. Software projects, Lisp. And we have AFP, PAIP, our exercises. Oh, We don't have any of that here. Okay. So we mainly focused on, just to give you kind of a heads up here, if we go back to this here, we can actually go and recall. We created our own equations dealing with initial values, and we've actually went ahead and dealt specifically with floating point numbers here, if you recall, because we were dealing with certain situations where um, the actual and I'll give you an example of this. Once we load, let me just go ahead and load our 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 ASD here, and then do set package so that we're always in PAIP, and then let's go ahead and requires student here, and now we have that, and we can actually go ahead and run the following example that we've done. Um, Let me see if I can actually find. So I thought I saved the buffer when I actually did this. Give me just 1 second here. Let's see, what did I do with that file? We actually, well, it doesn't really matter. I can go ahead and create this very quickly. Um, so we had the following problem that we encountered originally, which is hold on 1 second, let me just get this here. Okay, and we could just go and do that. Okay, and we create a list of this here, wrap it, a parameter word problem. And what we're doing here is we are actually going to go ahead and put our issue here. So if you recall, the the period and commas and percentages are all special characters, and periods especially is a Lisp special character in that it actually denotes a dotted product. So we have to actually emphasize that this guy is uh, it's not a dotted product. Okay, it's not a cons pair essentially, where the car is going to be the first part of the pair and the kidder is something else. And if you recall specifically for comma, a comma are actually unquoting operators. And if we end up having commas in here, it'll end up thinking that you're trying to essentially unquote something inside of a macro. And since commas do not have special meaning in sentences, we needed to make sure that that gets handled accordingly. So we have something like this, all right, and we could actually call um, the word problem solver student words. So we can actually say student word problem, and this will end up going ahead and correctly now marking the floating point expression, because what we did last time, if you recall, we created this function called create equation that basically checks to see if the first part of the expression is an atom, and um, we are handling the rest of the expression as being a set of symbols. And if it's not any of these, then we can go ahead and reduce the expression. But if it is one of them is a symbol, like a period in this case, or in our case, uh, it's going to deal with a specialized symbol, which is 69.70. We will go ahead and then find the symbol, convert it into its floating point equivalent, and then what we will do is go ahead. Well, what we do is we find the symbol, check to see if it is a floating point by reading the symbol name. And then if it is an actual floating point, we then go ahead and find a position in the expression where the symbol exists. We convert the symbol into an actual um, value. And then what we will do is we will actually replace the symbol with the actual value and then return it. So this way, you can actually handle um, the case where you have a floating point expression. And there are other equations that we can end up having to actually handle that too as well. And then we had to, of course, update in this case our create list of equations to actually go ahead and handle this particular case. Okay. So now, instead, originally this read has if Adam first expression, just return list expression. But now what we're going to do is we're creating an equation of the expression, so that way we can handle the special case with floating point numbers. So that's all well and good. But one feature that I thought would be interesting to add to this, and this is actually problem number 1 in Chapter 7's exercises, and that is dealing with solving linear pair of equations. Okay, so um, let's say that we wrote um, the following equations. Okay, um, set of equations, so to speak. Okay, so def parameter uh, system of linear equations, and we'll create the following list of linear equations. And this is according to what the book has. So we have 100 equals, and we need to put this in special characters. Actually, yeah, this is a special character, so we need to go ahead and handle that accordingly. Because I believe right now equals cannot be used. No, I can actually go ahead and use that. Equals, what is the equation? Yeah. Uh, Let me put that and that there. So now we have overhead, overhead plus, there we go. So we got this over here on this side, and this over here on this side as being, again, we're quoting these because we don't want to, because parentheses mean something in common lists, we need to make sure that we have those actually accordingly set up. Running times 40, and then, so this is our first equation, and our second equation is, of course, going to be dealing with our, and I'm going to just go ahead and use the period as the separation of the equations. And then we have our second one, which is overhead equals 10 times running. Overhead equals 10 times running. Okay, so if we wrote this way, okay, and we try to pass this into solver, okay, so just to show you what this looks like in our thing, it looks like this, okay. Ooh, this is actually not looking right because it is eating, right, so I have to actually go do this, sorry. I have to go convert this here and put this here. the space in between them so that it eats. Okay. And go. So if we have that, we can then do this. Make sure, and then let's go here. And it looks like this. Okay. If we try to, let's see, pass this along, the student right now as it stands. Let's see what happens. Okay, solve the equations. What ends up happening is something like this, which is wrong, which is it's looking at 10 times running. Overhead equals 10 times running. Let us add no parentheses. See what happens. It looks like it doesn't like the parentheses at all. Okay, let's delete these. Actually surprised that it didn't do that. That's okay. I'm not totally surprised that this will happen. So we're gonna have to hopefully respect PEMDAS, and we have everything correct. Let's see what happens here now. We run this, you end up seeing something like this. Okay. There's no solution because of the fact that it was unable to recognize that overhead equals 10 times running, so could have easily substituted overhead with um, uh, 10 times running and then solved for running, and then we could have solved for overhead. So how would we handle this? So let's think about this for a minute. And by the way, this is going to be a free for all for those of you who are following along. Um, Anybody who's on the stream, who's watching, feel free to ask questions. I will answer them as I, you know, periodically look at the uh, the chat. Okay, there's no questions. So let's get started here. So the first thing is we need to look at how we are determining um, the concept of one unknown. Okay, because this is kind of the key to this. This one unknown equation, just to give you guys a heads up, is what ultimately is used to determine whether or not we can substitute a particular expression inside of another. If and you can see that here with uh, not isolate. Where is it? It was here, one unknown. But what we really need to talk about is one variable um, if one variable is written in terms of another. Okay, and so we need to look at what one unknown does. So what does it mean for something to be an unknown? Okay, is it a symbol? Okay. So the first thing we could do is, and let's go and do this. The first thing we need to do is probably determine one thing. Well, an easy way to do this is you know that you could an expression is substitutable if there are exactly two unknowns, all right, in the equation followed by an equal sign. Okay, this is probably the dumbest, but it's the easiest way to probably handle this. So you're parsing the expression, you're checking to see if there's at least two unknowns. One of them is not, and if it's greater than two, you have to check to make sure that what is it? Um, if uh, if one of them is an operation, an operator, followed by um, two of the expressions, because again, we're writing these expressions like the following. So let's break this down first. Let's go grab our list of equations after they've been translated. Okay. Um, so let's go ahead and do that. Diff parameter um, equations list. Let's go create list of equations. Translate to expression. To expression. Remove if noise word p, and let's use solo the system of linear equations. Okay, so now you do that. What is our equation list look like? Okay, so let's write a function called that takes the expression, okay, because that is an expression, um, and say is substitutable expression. Okay. Now, obviously, I'm going to say up front, you can totally write this in various ways. This isn't going to handle um, the case of three or more variables where you have to essentially go through multiple substitutions before you find a variation of an expression that can be solved. This will handle though essentially what I would consider to be a triangle problem. All right, a triangle. Most of you know in system of linear equations, if you have a triangular matrix, if you're able to reduce it into uh, uh, a form where the last expression has some sort of constant value, you could then solve each of the values above it. We've already most of that already exists here. The only thing we're doing here is doing one more thing, which is uh, updating the expression and then rerunning solve equations. All right. So and so let's do this first thing, which is creating a function called is substitutable expression exp. Now here we need to check if, again, if the expression is an atom in the first part of the expression, which obviously it will be, okay? And then if it's not, if none of them are symbols, so it's the same kind of check that we had before, okay? And not, if I can actually type today, AM, XY, and X and Y, okay? Now we need to do map car on symbol P, rest exp, and then we need to obviously pass an initial value, initial T. Okay. Exp else. So now we can hit this other case. We need to check to see. Oh, what am I doing? We're gonna make this into a else. And we could probably write this better with the cond, but I think this might make things a little simpler. Actually, you know what? Instead of writing it this way, let's do it this way. Let's write it this way. This would be much easier. And if and atom is the first expression, and what we have is in the rest of the expression we have two unknowns exactly. So how would we know that we have two unknowns? We can actually count if, okay, if symbol, okay, count if symbol on the expression. So let's see if that will work. Let's go ahead and get ELT equation 1 and see that we got that. So let's go ahead and do count if symbol P on rest of the dat. That's 1. Wow, wait a second. Interesting. What is first? Hold on. If symbol P ELT equation list 1. So there are two symbols. Oh, right. In this form, when we get the expression, this is handling the equal sign as an operator. So we don't even need that. We can actually just simply do equals 2. Okay, so now let's go ahead and do that. And let's do is substitutable expression on ELT equation list 1. Now, what's going to be interesting is in here, technically, this is going to do the same. It's going to make the argument that both of these are substitutable expressions, which is actually not true. At least, if I wrote it correctly, if I understood what I wrote correctly. Oh, interesting. That's good. That's good. Excellent. How many it's so now I'm kind of curious. Count if symbols ELT equation list 0. There's exactly one unknown here, according to that. That's interesting. But there are 2 unknowns in this case. What is it catching on? So I'm curious as to what's loop for sim in ELT EQN list 0 when symbol p sim collect sim. What exactly are we getting? Oh, so what are we getting here now? I'm kind of curious what we're doing here. So a lot of this here is going to be trial and error, mainly because of the fact that we need to first correct to see that we're getting correct substitutional expressions. So I'm doing some exploration here just to see what it's trying to do. Uh-huh. So it's counting. Okay. So this is actually not getting everything. So when we do, so the reason why this was, I kind of figured that this is wrong, is this looked too good to be true, is because we need this to correctly look at so this alone won't work because what's happening is in the case of 10 plus running, let me just pull up the equation list, it has its parse here again. Okay. Hold on, for some reason my So let's bring this up here. EQN, sorry, EQN list. Okay, okay. So the reason why this is happening is the reader, the Lisp reader, is treating the second parentheses has another expression. So what we have to do is write a recursive function to actually do a count of expression, count of nodes. So what we'll do is um, we need to write one more function. We may want to just do this in a labels, but we will see what happens here. Yeah, that might be better. Let's go ahead and write a labels. Labels. Oh, what the heck am I doing? Here we go. Labels. Okay. And labels allows you remember, it allows you to write recursive functions that can call on themselves. And let's see here. So we do um, let's say count expressions. Count expressions. Sorry, count symbols. Let's call it count symbols. Symbols. EXP. Now, the base case is if uh, let's do count symbols X ACC. Here we go. If the current thing is not a symbol P, then we hit the end of our, oh, well, if we're doing if not, we can actually write this as an unless. Okay, no, go ahead and write it this way. Say unless simple P exp acc. Otherwise, oh, so that's right. We can't write it that way because we have an else case. So we're gonna have to say, yeah, if not symbol P exp acc, otherwise we do when it is a symbol, we do plus oh, so if it is a symbol, we get 1 plus whatever it's going to be dealing with. So so the ACC is going to be incremented, but we need to also deal with the case where there may not be it'll be a constant, so it may not be a symbol after all. It might be an atom. So we need to check to see that we do not, let's see, we could do this. If not symbol, if it is a symbol, then um, do the following. Do count symbols increment, oh sorry, rest exp increment and what I should do really here is this first is what I need to bring up. Okay, ACC. That should be it, but we shall see. Then, of course, we need to call it. So we need to do count symbols and on exp, and we can actually do bcpwr equals and I can always rip this out and make it into its own function at some point, just to test it. Morning, oh, wait, oh, right, sorry, I have to do this. That's what I needed. Okay, so now let's see if I could get is substitutional expression working the way I expected. 0, nil. Let's see what this is. 1. This is also true. But is it really true is the question. So, let's count symbols. Let's grab this function here that we wrote. Okay. Paste it. Oops. No, 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 no. That's not what we want to do. Paste it. Nope, nope, nope. That's not what we want to do. Okay, let's go ahead and do this. And that here, count symbols on ELT equation list. 1. Oh, right. Keep forgetting that I made this into a recursive function. Okay. 2. Okay. What is it counting on? So let's do this first. Okay. Let's go ahead and first format and say parsing expression tilde a tilde %sign exp and see what it's actually parsing. Oops, am I dealing with drive types as values? So we need to, let me do print instead. Oh, wait. T. There we go. I'm an idiot. I forgot forgot that I have to, with format, you have to specify standard out through the T variable. Count symbols. Let's see here. Boom. Parsing. Overhead. Okay. So it's not recognizing that it needs to actually parse the internal expression that it's getting. Okay. So first we need to do this. If not symbol. So what we need to first do is we need to wrap this around and first do cpwr if I'm wondering if there's an operator that we know if it's one of a dictionary if is operator. Let's see. We don't have that. We don't have operators here. When we solve the equation, how do we solve it? We isolate some stuff here. If EQ, if an expression XRX. Let's see what this is. Um, okay, so this function here, I see. What I could do is we could create um, a list of operators here, like this def constant. Let's say arithmetic operators. And so this way we can check to see if it's a valid arithmetic operator. So plus, minus, times, divide, equals, maybe even add expt. We can deal with exponents too as well, but we'll handle with the basic operators for the time being. Okay, so we have this, and then naturally we're going to make a defun arithmetic op p, and we just need to check to see if this function takes in an op, and we check to see if the operator is in the list of arithmetic operators. Okay, so we have that. Let's see what this does just to make sure we're not going crazy. 1 second. Documentation member function. I thought it was checking to see if something is a member. Return to tail of a list with the first satisfying. Oh, it's returning the tail. So we do not want it to actually return anything. So let's see. We just want it to return true or false. So what we want to do is actually do the following. If here we go, true, otherwise nil. Oh, I don't even need to do that. Let's do this. When true. So this should work. So if we do member this, we get true. If we give it something like, say, POW, we get nil. Perfect. So now we have what we need. Let us go back to our count symbols here and say if arithmetic op p on first expression, then we don't actually count that yet. We actually go in and we count symbols on the rest of the expression, but with the accumulator unchanged. Okay. But if it is, we go ahead and we grab we increment it and we move on. So this should now do something slightly different than what we had before, and we'll go and update the code once we have this all working. Let's go back to our call here, and it caught that, but it's not actually going into the else case here, which is parsing the secondary expression, because it is technically not a symbol, but it is an expression that needs to be. So what we have to do here is make one adjustment here. If it's not a symbol and it's not a list, then we can actually go and deal with that. So C, and because this is going to be a list P, right? So we need to check to make sure. List P. First object. Otherwise, what we need to do is and in here we also need to make sure that we're handling the case that it's not it's not a list too as well. I mean, if it is a list, we need to go and just not accumulate. We need to continue parsing. There are other ways of handling this, guys, but this is me kind of traversing through the actual expression itself, just to make it easier to get an initial implementation, then we can always tweak it if we wanted to. Okay, so list expression first. Okay, let's see what happens here. Now, so why is that still giving me a 1? So it's not actually parsing. If you're noticing, it's actually hitting this case where, so let me go ahead and look at this. Format T first exp is tilde a tilde percent first exp. We really want to know what the token is that we're actually looking at. So let's go ahead and see that. What is it telling me? Overhead first expression is 10 dot whatever. Okay. And now I'm kind of curious. Is Lisp P saying, oh, dummy. There we go. And we hit this case. I kind of figured that we'll hit the infinite recursive loop. It only takes a while to do a dumb thing. Let's see if I could do slide top level, restart Lisp, because that will happen. Okay, so we're gonna have to do this again. Oh, sorry, what the heck? Ooh. Don't know where that came from. Okay. Okay. Let's see here. Oh, right. Let's go ahead and do requires student. Okay. If it's not, oh, if, and I know this is bad because I'm basically doing De Morgan's. We can actually write this out things, but I wanted to make it as tail recursive as possible. Say it's not null. Or no. It's actually an or. I forgot. It's or. Or if the expression is null, which means we're done, or if it's not null and it's not the expressions that we want, then we can actually go ahead and go to the ACC. So we're done at this point. Let's see what happens. Undefined. Oh, right. Make sure. Okay. Let's go ahead and go to. Oh, right. Sorry. Let's first go here and get our equation list all verified. Okay. 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 Is done. Done. Okay, what happened here? First expression. Oh, arithmetic boundaries is unbound. Okay. I did not realize that. Okay. Hmm. So it's parsing first expression. First expression is null. Why is first expression null? Because the expression is. Oh. Got it. Got it. There's actually one more layer here. If so this can't be written this way. What we have to do is we have yet another if that we have to write. So let's go ahead and do this. CPWU. Okay. Delete this guy. And then here, what we do is we have to parse the first expression and then we need to parse the rest. So what we'll do is we do this. We do progn cp sf, okay, and we do not progn, we do yeah, we do progn, we do when, yeah, we do progn, we do the following, we do when Lisp first exp, then we have to go in first count symbols on exp acc. Okay. Then we need to go and grab the next set of symbols. Because what we're doing here is we're grabbing the current symbol, that means the current expression, and we're counting how many symbols there is in that expression, and then we have to go and grab the rest of the expression and get the rest of the information. Let's see if this one gives us something slightly better. No, control stack. I kind of figured that that is exhausted. Okay. Mm. So this one, what would force this? We need it to nest into each of the individual. So what we're essentially doing is we're writing a parser for nested expressions, and we're counting the number of symbols inside of this expression. So what can we do to prevent this from actually doing that? We let's try to write this iteratively, shall we? Might be the fact that I'm not able to do this correctly in do list. Let me see if I could do symbol exp and print sim. Simple dumb function, declare, ignore, just so that we, for the time being, we're not going to use the ACC. Um, okay, let's see what this does. Okay. Um, so what we have to do is we have to think of two cases here. So we do let's do this, and let's do this and say unless list p exp print, else count symbols exp acc. Let's see what happens here. Oh, sorry. We take this guy out because now we're using it. What happens? Exhausted. Why? Oh, not unless list. When? No, unless list is correct. Let us do this. We need to do this. Simplify this a little bit. Do format t symbol. Ooh, I heard a question here. Oh, see this here. Oh, okay. Let us do this. So the symbol that we're going to be looking at is a, and we need to know obviously if it's a, so I'm going to get rid of this guy for the time being. So for those who are just joining us, what I'm doing is I'm trying to add an extend student, the word algebra problem solver that we've seen, um, with the ability to be able to essentially deal with systems of linear equations, where we have substitutable expressions. So then we could solve the system of linear equations with the substitutable expressions. This is a little bit more involved, but it requires us to actually extend what's currently there with just the small ability to first figure out if we have a substitutable expression and then go find where that symbol exists in the other expressions and then substitute it and then see if we could solve those equations as is with the one unknown approach that we currently have. Um, so just give me a second here. We're kind of getting stuck with kind of parsing nested expressions. So that's kind of what we're currently working on. List exp or list symbol is kind of what we really need to look at. Tilde a tilde present sim list p sim. Okay, let's see what happens here. Okay, so based on this, what I need to do is, let's see what I wrote originally. This needs to be changed unless the symbol is a list. Print it. Otherwise, go in and parse that guy. And yes, it's called count symbols, but it's really printing symbols right now, just mainly because I'm trying to make sure that I'm able to continue down the tree. And I'm just basically writing a basic tree walking algorithm. And I, of course, use the declare ignore, so I'm going to go and change that. Okay, let's see. And kind of figured that was going to happen. Print, print, print. Oh, let me. That's right, because I need to make sure that this guy is only called when it is a list. Go ahead and traverse it, otherwise ignore it. Okay. So it's in the same. What? Hold on, do I have unbound parentheses? No, I don't. Okay. And it's still blowing up. Right. I'm blowing it up because of the fact that it's not able to iterate through all of the symbols, right? So why is that actually encountering here? Did I mess something up in my ability? Hold on, let me just see here. Okay, the first time it gets equals, it hits it. Oh, dummy, 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 dummy. My call needs to be on the symbol. No, 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 not that. This guy. Sim. There we go. Now this should work. Okay, boom. So now what we need to do is here we need okay. So here we do increment ACC. Oops. Okay, so now we're calling it. We're incrementing the accumulator each time we find a symbol, and then we just pass this on to the recursive call, which will then keep on incrementing itself. So this should keep going until we hit the last case, in which case we just return it, and that should be good. Let's see what happens when I do that. And we get 2. Boom. Exactly. What? Wait a second. Unless or arithmetic operator OP sim print sim. I'm using the print just to see what we're printing, what we're counting. Okay. And let's see what happens here. Okay, so it gets running, but running is not counted for some reason. Print 10 increment F. Oh, curious now. Is it because I'm doing this recursively, but I'm not actually incrementing it here? There we go. Iterating, but it's not. Oh, this is odd. We don't want numbers to be included here. So let's go ahead and get rid of that too as well. And we still get 2. Very nice. So the reason why we were getting 3 technically there is, but it's not counting, is because of the fact that we're not doing like a set F on ACC because we're passing it in. So like I could totally do something like this, and maybe this would do essentially the same thing. If I did setf ACC incf, okay, and then do that, and then CPWU this, and get, oh, sorry, ACC, okay, oh, interesting, it's not recognizing that, okay, oh, let me do, not incaf, let me do 1 plus, oh, there's a oh, because it's passed by value, it's not passed by reference, it's not a con cell. We're passing it into a function. Okay, I get that. So we need to always pass in the incremental version of this. So whether we do it this way or the other way, we need to actually go and account for the fact that we are dealing with a symbol that we found. Let's see here. That's weird. I had assumed that this can actually take in something. Okay. Let me do this. Let's see if I could do this. It is being passed in anyway, so why is it? Hold on one second. Let me see something here. Incf acc print acc. Let's see what happens here. And let's see what it prints when we first get it. So we know that we called it, we know that we got it. Okay. So we get this. Let's see. ACC 1, 2, 3, 2. Okay. So ACC gets 1. Let's see what happens when we do this. Ah, I see what's happening. It's because of this last expression here. This should not return. I think the last expression is what ends up getting returned. CPW, sorry, FS, MMCF, there we go. Let's see what happens if I do this. Okay, so we do get 2, but it's not actually returning. So, let me see what if I could do CP WR, see if I could get this to return. No, it's not actually returning anything. Yeah. So we're now incrementing, we're getting it done, doesn't realize that it needs to return. So what we need to do is we need to grab this increment here. and we need to set f that into so we need to do this. Setf ACC with the count symbols of ACC. There we go. To force it to do what it needs to do. Okay, so we now have our count symbols correct now. It's going to go through, loop through all the expressions. The only time that we're going to ignore symbols is if we have a list, which is a nested expression. We have an arithmetic operator denoting a arithmetic, like the name says, an arithmetic operator, plus, minus, or times, divides, or equals, or if it's a number. Now, the one thing about numbers is I don't know, I believe it handles all generic stuff too, including floats. Right. Um, so that should handle both floats and integers. Okay. So now we have that. Let's go back to our count symbols that we wrote originally. Where's our labels? There we go. We're going to replace this guy and do this with our scratch buffer version. Boom. Okay. And we're going to get rid of this. Then get rid of this guy, which is our old version. Fix formatting. And since we have some stuff here, we could do this. So we can actually look at the code in a single buffer. All right. So now we have that. And we now know whether or not the substitutable. So let's try. So this one will do the same thing as before. So like I said, we have two what could be perceived as substitutable expressions. Now, the one thing to be aware of is the way this is written. This one will, both of these will be treated as the same. Okay, they'll be both treated as substitutable expressions, which is technically wrong because this one is defined one in terms of the other, whereas that other one is not. So we need to tweak this this predicate to being a little bit more than just this. We need to write it in such a way that we have a left-hand side and a right-hand side. And one way of dealing with that is honestly we could write this another way. We can actually say if the left-hand expression, okay, is an equal sign where so this could also be written this could also be written a different way because it can't just be the count symbols. Okay, so I'll show you first off what this is going to show us, and this is going to be an incorrect thing because so this is going to be nil. So this is true, but that's nil. But why is that nil? That should not be even nil because it must be. So now I got to see how many what happens when we run count symbols on ELT EQN list 0, starting with 0. See, this is giving me 1. This is also giving me 2. This is giving me 2, and that is also giving me 2. So yet, oh, it's because I did not update the substitutional expressions. So let's do that. That's true. And if we do this again, this is also true. So you can see that this even though we counted the number of symbols correctly, we are actually still nowhere near where we need to be, because we need to check the left-hand side of the equation and right-hand side of the equation, really. So what we want is we want the equation to the predicate to being the following. If we have if and okay so we should really write this as a cond. Cond if arithmetic AR operator first expression, then what we need to do is we need to go in and look at the rest of the expression. So we need to do is substitutable expression on the rest of the expression. Okay. So that's the first case. Okay. Let's do this here, because technically we could make this smaller for the sake of simplicity. Is substitutional expression. Okay. Obviously we want to put this dash p because this is a predicate. The second case is going to be, well, if and the if the left-hand side is symbol, so that's our first of the expression, and the right-hand side, which is the rest of the expression, is going to be a list with one unknown. So really, we need one unknown on the rest of the expression. Then we have a valid substitutable expression. So this is a true. All right. So now we need to write the default cond for this, which is going to be, shoot, now I'm having a brain fart, the true case. Um, for all other cases, we're dealing with nil. So in this case, we have um, is is subs xp ELT EQN list 0. This is nil, but this is so close. What am I missing here? The rest of the expression should be nil. But it could be because it's not recognized. The rest of the expression might be a list. So what we need to do is we need to do the rest of the rest. So if and this needs to be handled in a slightly different way. So we need to be able to get the one unknown from the rest of the expression. So how do we do that? We need to not an genetic expression because we're losing it. Let's see how the one unknown is written. So maybe we could get some inspiration here. Okay. EXP RHS exp. We can actually get that. Okay. Let's do that. If what is no unknown doing? If no unknown expression, if it's an atom, forget about it. But if it's a symbol, so got it. What we have to do is here. No, this is fine. Do exp RHS of expression. And if the left-hand side of the expression exp LHS of the expression. Okay. G. Let's see. This is still nil. Why? Let me try this. If no unknown here. Oh, if one unknown is on the left-hand side and one unknown is on the right-hand side, then it is a substitutable expression. That's kind of what we need. This is nil. Huh. Why is that? Oh. I could write this way. Let's do it this way. Okay. Do it here. Good. Let's try that. Okay. Ooh, why? Let's see. What is getting handled? Okay. How about okay. Here. Got it. So since I'm eating it, I do not need to do this. This is not needed. If that's all I need is this one. Oh, ooh, no. This one case here. Really. Now running. Do this. Instead of using cond, just simply say when and t. Okay. This is nil. True. There we go. Now we got it working because the left-hand side overhead equals, the right-hand side has one unknown, and then we're good. So whereas in this case, the left-hand side is 100, the right-hand side is our actual expression, so we can't actually deal with that. So what we now have to do is we need to, and I I'm surprised it took me this long to actually get the expressions down correctly, but um now that we know what this is on the left hand side being one unknown and the right hand side being one unknown, the next time what we'll do is we'll actually go in and change and run a substitution on all the expressions where this one variable in this case is our overhead um, and we'll replace it with 10 by 100 10 by running, and we'll end up hopefully being able to actually solve for running. But then the next step is obviously then solving for overhead afterwards. So um, there's still some little more work in this, but you can see that it's coming together as we come along. So tune in next week when we actually start dealing with the second part of this, which is the actual substitution and solving, and then hopefully we can, time permitting, we'll be able to finish that off. Um, but we debug along the way any new interesting things. Um, that's it for today's episode. Are there any questions in general about Lisp or what we are covering in terms of word problems? Okay, thank you all for joining tonight. I hope you enjoy the rest of your Monday night. Um, I'll see you later. Bye.